Hello everyone, my name is Gerardo Vitagliano and this is the presentation of Pollock, our data loading benchmark. As some of you may be familiar with art, you may recognize this painting is from Jackson Pollock, the famous American painter that inspired us to name our project after him. In fact, sometimes real-world files may look just as messy as his paintings. To give some context, in traditional data-driven workflows, there are a plethora of existing systems used in different stages of a data pipeline. For example, programming frameworks may be used for data preparation or analysis, database tools may be used for data storage, or user interactive tools may be used for data visualization. All these systems have different internal data models, different connectors, and different interfaces, although data has to flow between them. Now specifically, if data is relational or tabular, very often it is created, stored, and distributed using tabular data files. Tabular data files are widespread and very commonly supported by many applications. Typically, they are very easy to parse as they are just plain text files. Think about CSV, TSV, or the likes of it, where a few characters have some special meaning, like commas to delimit columns or quotation characters. They are also flexible because their format can be tailored to suit specific needs, but because of this, there exists no real standard. There are some standards, like the one defined in the RFC or W3C specifications, but we could define these as descriptive because they describe the most commonly used format and they do not prescribe any specific parsing strategy. Specifically, we surveyed over 3,700 real-world files publicly available, reported to be in CSV format, but we found that very often these files do not follow any of the standard whatsoever. We looked for and identified a wide range of structural issues that have to deal with how the files themselves are serialized rather than about erroneous values in their data. For example, many files contain multiple tables, multiple header rows, or have an inconsistent number of cells within different records. In other cases, there are missing characters that are fundamental, like quotation or escape characters. So what happens if users have datasets of non-standard files and they simply try to load them into any tool? Take for example this real-world file with a non-standard structure and try to load it into Pandas. This is what happens. In this specific case, the tool complains about an error in line 97 where instead of 25 columns, there are 27 columns. So the end user either has to go back, prepare the file, or to tweak the system configuration, if possible, to properly load this file. This brings us to our fundamental question. Can we systematically benchmark how good systems load files that have non-standard or problematic structures? What this would mean is to take into account all of the structural inconsistencies and evaluating how they affect all of the different systems that play a role into the data-driven workflow that I've shown you before. So here comes the Pollock benchmark. Pollock does not only reference the abstract painter, but also stands for Polluted CSV Benchmark, because we call pollution the fundamental process with which we benchmark data loading systems. First, we take a representative clean and standard source file and pollute it by injecting structural inconsistencies such as the one that I've shown you before, creating a polluted version of the file. And then we load this polluted file into a system under test. What we would like to benchmark is the parsing algorithm of the system under test, which we define G-1 of SUT. But in general, we do not have access to the internals of the system. So what we do is to generate an output file using the standard RFC CSV grammar, and then we compare the output file with the input file. Considering that we know that the polluted file grammar, because we produced this file, and we know the output grammar as it's the standard RFC grammar, we can compare the content of the resulting output file with the content of the input file. I would like to give a little bit more intuition on how does pollution work and how do we systematically create these polluted files. we consider data serialization grammars as context-free grammars that can be used to produce a file out of a content or to parse a content out of a file. In any context-free grammar, we can identify three different groups of rules: formatting rules, content rules, and structural rules. Content rules are the ones that resolve to multiple terminal symbols. Specifically, any serialization grammar will need content rules that resolve to multiple terminal symbols, otherwise it would not be possible to express information. In the example grammar G of this slide, the content rule R4 states that the column name can be either ID, product, quantity, or so and so. On the contrary, structural rules must resolve to only one symbol. They have to be present because otherwise the grammar itself would be ambiguous and it wouldn't be possible to serialize or parse content from files. One example of structural rules for this grammar is R7, stating that the column delimiter has to be a comma. And then, finally, we have formatting rules that put content and structure together and specify how to format content with structure. So if we have a look at several different tabular files, what we often find is that they are serialized with slightly different variation of the same grammar. We call these variations grammar dialects and define a grammar to be a dialect of another one if it's different in its structural rules. So if we consider, for example, file F0 and file F1 in this slide, it's clear that they have the same format and they also have the same content, but their structure is different. In this case, they have been serialized with G0 and G1, which are two dialects of the same grammar, where the delimiter rules specify the use of semicolon for G1 rather than comma for G0. So we define our benchmark to encompass all of the possible dialects for the survey files that we manually annotated. We define a list of pollution that replicates all of these grammar for a total of 2,289 polluted files. But finally, how do we evaluate how well can the system load these files? For each polluted file of the benchmark, we calculate 10 numbers, starting with success, the most important number. Success is a binary score equal to 1 if the system can carry through with loading and does not halt the loading process. Otherwise, we give the system a success score of 0 and consequently, we zero also all of the following metrics. If the loading is successful, we then measure precision recall and F1 at the header, record, and cell level. Why are all these scores necessary? Consider the example file on the right of this slide. The output is the results of loading this polluted input into pandas. And as you can see, pandas includes a spurious header saying unnamed 0, unnamed 1, and so on. In this case, even if all of the cells are correctly loaded and all of the data records are correctly loaded, there is some spurious information that would be reflected in a lower precision score. On the other hand, if the system is missing some of the original content, then the recall score would be lower than 1. We also combine the precision and recall into the F1 score. Regarding record and cells, it is important to measure precision and recall at different levels because in some cases, for example, if a column shift happens, a system may load all of the cells in a different column, which should also be considered an error. We measure these scores for all of the polluted files of our benchmark, and then we average them with two schemes. The first scheme is a simple weighting scheme, and the second scheme is weighted by the natural occurrence of the given pollution in the original survey. So if a particular polluted file is more likely to happen in our survey, the corresponding score will be higher in the final average. The final aggregated score is a number from 0 to 10, with 0 being the worst and 10 being the perfect score. To conclude this short presentation, let's have a look at the results of our benchmark, which is the slide that you were most likely waiting for. For time reason, here we only present the summary result of the Pollock benchmark with the aggregated score. I very much encourage you to refer to the full paper for a more detailed breakdown of different polluted files and an in-depth analysis with takeaways, both for end users as well as for system developers. What I would like to point out in this presentation is not much a detailed analysis of the 16 systems that we benchmarked, but remark how the Pollock benchmark is applicable to 4 different categories of systems and perhaps even more. Specifically, we have tested CSV data loaders with specialized algorithms and parsing strategies, relational database systems, spreadsheet systems, and data visualization tools. I would caution to compare systems across different categories, but it's useful for end users to compare systems within the same category, for example, to select the system with the highest score. Also, a very important measurement is the time to load the files, which we measure in milliseconds. As you can see, obviously, graphical user interactive systems such as spreadsheet systems or data visualization systems usually have a higher loading time because users have to configure or click through all of the options. I would like to mention that the benchmark score of these systems have been obtained with the best effort loading strategy. So if the system allowed for automatic detection of some parameter, we use the automatic detection. Otherwise, we resorted to manual configuration of all possible options to correctly load a specific polluted file. Finally, let's wrap this presentation with a quick overlook into opportunities and future work. First of all, I encourage everyone to visit our GitHub page where we open source all of the code to reproduce our benchmark, our survey with the annotation, and the scripts to implement the benchmark for your own systems under test. So my hope is that this benchmark will keep growing, including more and more systems and perhaps even more pollution. Moreover, I can imagine this benchmark being applied to measure data preparation algorithms in terms of how much do they improve on the Pollock score, or for example, to profile structural metadata of CSV files in terms of their pollution. In the future, we can also scale the benchmark to have a dynamic pollution space. So for now, we have a static list of polluted files, but it would be interesting to tailor specific pollutions to a specific dataset if users have a different distribution of real-world files, perhaps by adjusting the weight of the final aggregated score or by including different pollution variants. Another interesting direction to follow is the combination of different pollutions on a single file to test what happens in the case of interacting pollution. Finally, the pollution framework can be extended to other data serialization and parsing grammars, for example HTML or JSON, which are also based on context-free grammars, and perhaps can be applied to benchmark other categories of systems. With this, I would like to thank you for your attention and feel free to reach us anytime via email or on the Pollock GitHub page.